Hey Zohad, how are you doing?
I'm good. I'm great. How are you?
Good, thanks. So could we get those who maybe haven't been to this session before to introduce themselves? Derek, could you give a quick introduction?
Yeah, my name is Derek. I'm here at the main office for Pyrofex, and I'm doing the formal semantics for Rolang in KFramework. So,
Awesome, glad to have you.
Are you the one that made the commits in the RChain repo with the KFramework stuff?
yeah, the one just last week.
Nice.
So
Yeah, I was really excited, and I shouted about that in this group and pulled it up. So
yeah, so hopefully, I'm working hard on it, and hopefully things will develop in a reasonable time frame.
awesome. Hey, could I get everyone who isn't speaking to please mute? There's a lot of clicks going on from your computer, Roland, and a couple others. Thanks. Let's see. Is there anyone else here who hasn't introduced themselves that would like to? Zohad, have you been to one of these sessions before and introduced yourself?
I haven't been to one of your sessions before, but I've been to Greg's lessons, both of them.
Okay, great, awesome. Would you like to give just a quick introduction?
Yeah, sure. Well, I'm Zoat. Pyrofex invited me to the RChain conference in Boulder, so that's why I'm here. My background is I study econometrics and operations research, so a bit of math, a bit of computer stuff, and I'm really interested in blockchain right now, so that's why I'm here.
Awesome, glad to have you. What about Phil? Have you introduced yourself at one of these sessions before? If not, would you please? Thanks.
Hey, how are you doing? No, I haven't attended one of these sessions. So I'm Philip. My original background is in physics. And then as I entered the blockchain space, I shifted my academic focus more towards computer science. Lately, more focusing on game theory and mechanism design. And yeah, and then I joined RChain, as I think it's a great project out there in the blockchain space. And I'm also attending the sessions done by Greg. So, and I'm trying to catch up on this format here. So yeah, glad to be attending this one live.
Awesome, good to see you, Phil.
Okay.
I think that's all, but anyone please speak up if I am wrong. I see a lot of you in other venues as well.
So I guess David will join as well.
Okay, great.
Yeah.
Let me share my screen here. All right, how is that? Can everyone see that?
Yes.
Great. Okay, so like I've said in the email, Greg's course, Introduction to Design of Computational Calculi, that's closed and has limited participation, and I think the list for that is already set. I'm hoping that that's happening every week on Monday, and then I'm hoping to use the time that we have together. Could I get someone to mute here? There's some static. Yeah, I'm hoping to use this time every Friday to lead a discussion section, lead a discussion between everyone, and then also just sort of extend some of the material, especially in the direction of like defining things in KFramework, and maybe some other directions too. But I'm still happy to get your input on what you would like to learn together, and can try to focus things towards that direction. So I'm going to start with just like a quick review of the highlights of Greg's session. Or I guess actually before I even get started there, what questions do you have about Greg's session on Monday, or what sort of is still hanging for you there?
My questions start kind of near the end of the video, maybe the last 15 minutes or so.
Okay, cool. So like when we get into like the mathematical models of languages, or
yeah, and even for me, even the lambda calc part was pretty clear. Once he asked us to write the Scala code, for the row calculus, I think that's when it got a little trickier for me.
Okay, cool. I give some examples of Scala code in this lecture or in this discussion on of defining the pi calculus. So maybe that will help a little bit. The row calculus is a bit trickier than that, but yeah, maybe that'll get us closer. Cool. Anyone else? All right, so let's get started then. Yeah, please feel free to interrupt at any point with questions. So we mostly went over last week or last Monday with what a grammar is. It allows us to answer the question, is this a valid program? And often we represent our grammar in Bacchus-Naur form, which is a notation for context-free grammars. So those are two things that you could give a quick Google on if you're not quite sure what they are or want more background into them. Bacchus-Naur form and context-free grammars that could maybe give you some insight. So right now, the Erlang parser compiler is using a BNFC, which is a language for writing BNF grammars, a format for writing BNF grammars. And you can find that on GitHub. We've looked at that a little bit before, and that's a context-free grammar. That's a grammar definition. And the reason that what a grammar doesn't give you is it doesn't give you the strict meaning of a language. So it says how you can construct statements in a language, but it doesn't really say what those statements do. It can say that 2 + 3 is a valid sentence, but it doesn't tell you that what it computes is 5. So here's a couple examples of grammars that were given. There is an example of a lambda calculus grammar. These bars in between are sort of, you can think of them as ORs. So you can construct m and n either as an x, as a lambda x dot m, which is one of these things. So it's a recursive definition, or mn. And there's like the row calc one as well. So same thing. These vertical bars aren't the same OR because, yeah, it's a little confusing here, just given the spacing. But this is itself one construction. So the vertical bar is a construction in is a terminal that we use in this grammar. And this also has two parts to it. So it also tells us where these x's and y's can come from, which is they come from quoted processes. So what questions do you have at this point?
So I guess it's an obvious question, but like P and Q are processes or terms, and X and Y are names, right?
Yeah. Mm-hmm.
Okay. And do we know what like a bang does, for example, X bang Q? Do we know what?
Right. So just given this grammar definition, no, we don't. This is just sort of, we know that this is a valid sentence, but we have no idea what it means. In actuality, since we know more about the row calculus than just the grammar, we know that this is like a send. So this means we're sending Q on the name X, but that's not defined here, and we're not too worried about that at this point. Thanks for the question.
Okay, I also have a question. Greg said during the election that the P or X and Y now is well defined because we have to add P, and so it's more complete than the lambda calculus, which does not have this circle, does not say what X is, for example. Mm-hmm. What still is missing, it seems, that Q, nobody knows what Q exactly is.
It's right here.
That Q is the same as P, right?
Mm-hmm.
but nobody says it here explicitly.
It actually is explicit if you look at the left-hand side of this equation. So it's saying P or Q are constructed in this way. So it's like it's multi-headed. So P and Q are defined the same way, and they're defined by this same equation.
Okay, and therefore P is the same as Q, and also the last line applies for Q.
Yes, exactly. Exactly.
Mm-hmm. Okay, thank you.
Mm-hmm.
So I think that the reason we need both of them, like PQ, or on the bottom line we have XY, is just, correct me if I'm wrong here, is because some of these expressions, like P par Q, require two of them that can in general be different. Is that right? So that's why we defined like both P and Q there instead of just using P.
Yeah. So there's two different styles of doing these equations. So this is one style. And it might be a little bit more readable to let you know that P and Q can be different. But another style is you just have the type here, which is just like P, and then over here it would just be P par P. And that's also totally valid and doesn't change the language at all. Because yeah, these things aren't constrained to be the same P.
Cool, got it.
Yeah. So when we do some KFramework examples, KFramework does not support this notation of having, as far as I know, at least, it doesn't support this notation of having like defining two terminals at the same time. Or I guess those aren't terminals, are they? Two sort of grammar constructions at the same time, like that. So ours will look a little bit different. Okay, and then I guess I'll give a little bit of space here if there are other questions. All right. So moving on, we also looked at mathematical models of grammars. So here again is the Bacchus normal form of the grammar for lambda calculus, and then here's the mathematical model of the grammar. So when we're looking at mathematical models of grammars, we're thinking in terms of sets, like products of sets, and the disjoint unions of those sets. So what we're saying here is that there is this set M, which sort of given another set X is it contains every single valid term in our language. And the way we can construct that set is it's going to be sort of, we can break the set into three different components, which are given for these three constructions that we have up here. And then the number of items in that set are going to be given, and what those items are going to be given by the definitions that are between these plus signs. So here we have one way that we can construct a valid sentence is every single variable X sort of is a valid construction. So the set of X is one of those things, is one of those groupings that we have in all of our valid constructions. And then here, this takes both an X and another grammar construction, another program. So if we take every single combination that we can think of both X and a valid construction that we have here, that gives us the second part of our set. And then the third part of our set is every single combination of two of these together. So you can see that this is going to be infinite. There are going to be infinite number of items in this set, but you know, this gives us sort of a more concrete partitioning and a way to think about these grammar constructions mathematically.
So the plus sign operator is the disjoint union?
Yeah, yep. And so the The disjoint union, what that means is that say, well, there's a better example later, but we essentially have to mark each of these components of the set, because say there was another construction here that was like m par n, that was like another construction here. This would look like the same term in terms of like it would also be mx cross mx. But we need to mark those things as different because they're different grammar constructions. They're different terms in our language.
Gotcha. So Greg was using the term tagging, I think, right? Is that what you're talking about there?
Yeah, right. So that means that like each of these disjoint union, what it does is it means it's going to take sort of all of these things in the set and tag them, all of these things in the set and tag them. So we not only know, yeah, we can sort of add them together without destroying our duplicates.
I think this question might not be in the scope of the conversation, but if it, I want to ask it.
Sure, go ahead.
Between the lambda calculus and the row grammar, Greg said that pi calculus was somewhere in the middle. Is there an easy way to describe kind of the difference between pi and row so that we have an understanding of like why Meredith wanted to make row? I don't know. Is it worth knowing, or do you even know?
Yeah, sure. So actually, we've covered that in previous lectures for this course. So if you want to go back and watch those, I can sort of point you in the right direction. But the idea was that sort of like the lambda calculus, the pi calculus left sort of these variables hanging here, and by taking those sort of hanging variables and tying them back in as just quoted processes, it sort of closes the whole model of computation together. And we're gonna see some pi calculus examples in a little bit, and sort of compare them to the row examples, and then that should also be illuminating. All right, so oh yeah, great. Oh yeah, go ahead, Jacob.
Just saying thank you.
Oh yeah, no problem. Thanks for your question. Okay, so
I have a question about these pluses. So this MX thing is just the domain of where all this computation can happen.
The domain on where the computation can happen. So MX is a set, and it's a set of valid language construction. So that's the set that we're trying to define here. So yeah, I guess it's the set of valid programs in a language, which I don't know if that is the same as the domain of computation or not. That's not a term that I've heard before.
May I add something?
Mm-hmm.
I think what this is, it's basically, this is a way to construct a valid syntax. Mm-hmm. Not necessarily that this is the domain and that's the range, or this is the domain or that's codomain. It simply is, this is a way for a production in this language. That you have your non-terminals, which are the capital letters, and then you have the terminals, which everything else is explained in terms of it. So I think if you think of it that way, then we don't have to get into too much detail at this early stage. At least that's the way it makes sense to me.
Yeah, sure. That sounds right to me. Thanks.
Jake?
Yeah.
So I think also when I map this M bracket X, this set, when I map these to types, so if you wrote a parser with the parser generators, you would, once you parse something, you need to construct the abstract syntax tree. And this M of X to me maps to those types. So like X is of one type plus x times m of x. So each of those kind of maps to types, and so they, I don't know.
Yeah, you know,
So
thank
it's
you.
the set of all those combinations of when you actually construct objects, if you were implementing that, it's kind of the set of all possible collections of those objects. This is the way I visualize it.
Yeah, awesome. Thank you so much. Yeah, that will be, we're going to go over some examples of defining these same grammars in Scala code, sort of like Greg did, and that I think becomes clearer at that point. So yeah, thank you. Good look ahead. Okay, so we're still kind of sticking on the same topic here. I'm gonna have us go over a quick example and then take any more questions. So say we had our language S of X that had these two constructions. Either we could have sort of a lambda X or a triangle X. Can someone tell me what the mathematical model of this grammar would be?
So I think it's got to be the disjoint union of two different things, right? So something plus something.
Yep, great. Totally. So let's focus on the first thing, right? So it's going to be the disjoint union of two things, one for each of these constructions on each side of the par symbol. So this first one, you know, what does it require? We require I guess lambda and triangle in this example are both sort of static things, and then x's are our variables. I should have made that a bit clearer.
So it seems like the only thing you need for a term like that is the variable. So we might just do this with x disjoint union x.
Yep, great. Awesome. So, yeah, so...
Sorry, I have a minor question. I don't know if this is important or not. I'm not quite clear on what the big X in the square brackets on the left-hand side is. I know Greg was reading it as like S is parametric in X. I'm not totally clear what that means, though.
Yeah, so what that means is that sort of to have this language construction, you need some idea of what valid X's are. So you need to sort of import a set into this construction, which is the set of all valid variables.
Okay, got it. So it's basically just saying like, look, before you can do any of this, you need some set. Let's call it X. Okay.
Yeah, exactly. Derek, did you have something else to say?
Oh, all I was going to say is that it looks like from that second line with the like m bracket x line, that the only two options you have to use in these models are either x or m bracket x, and m bracket x is too big for either of those. So it seems like x would be our only option. I was just sort of going through the reasoning.
Okay. Yeah.
I have a question. We now have x parametric and s parametric in x is equal to x disjoint union x. Is that possible to simplify that to s is parametric in x equal x?
So yeah, that's a good observation. And this is sort of why I wanted to have this example, was because the disjoint union isn't just sort of taking it takes, so we're defining the number of items that can be a valid program. So if we think say we have a set of like 5 variables that can be substituted for x, I think it's pretty easy to see here that the number of s's that we can construct are 10, right? Because we can construct 5 different lambda x's and 5 different triangle x's. So what this disjoint union is saying is that the thing on each side of this disjoint union, we tag them so that when we put those sets together, the duplicates don't get squished. So the number of items in s.x is still 10 items, even though x has 5 items in it.
Yeah, Jake, for me, exactly, when you said 5 items, I was thinking, what if x were just a Boolean? So it could be true or false. So now it's 4 possible programs you could create.
Does that clear things up?
Yeah, thanks.
Okay, great. Yeah, awesome question. Good observation. That's what that example is there for. Yeah?
One more question about the big X. Is the small x an element of the big X?
Yeah. Yeah.
Okay, thanks.
Yeah, that's not written explicitly, but that's the idea. Okay, so now I thought it'd be fun to write a mathematical model of our PyCalc grammar. So here's our PyCalc grammar. We have sort of P's and Q's that are constructed by either a normal process, a par, replication, nuX. We've seen that before. And we have normal processes that are constructed this way. We have either a pi.p or a 0 or an mn. And then we have a pi, which is either like an input or an output. Any questions there, just on the quick grammar of PyCalculus?
If you could just link the older videos where I could review it, that would be great.
Yeah.
In the GitHub.
It's in the GitHub. You should see an index of all the. There's like a PyCalculus to Erlang tutorial, sort of a repo, and then you should be able to just see everything from there. And also the YouTube videos are all in a playlist as well. So if you look at my YouTube channel, you should see a playlist of everything. But yeah, I'll also work with you to link those together. So let's start just by defining pi. So pi needs to be parametric in an x, right? Because we need some x's here. And the construction is we have, they both can take, both the constructions take 2 names. So x's are our names, and we have an x cross x plus an x cross x. Now, using this definition of pi, can someone tell me how to construct the next step, our ends? So let's start with just, let's start with this construction here. What would be, what would we need to cross together to get this?
Go ahead.
So I guess we need a pi and a p. Can we use like a capital pi that's the set of all pi's?
Sure. So here we have, a pi, which our pi is parametric in x, and then we need a p. We can cross those together, and we haven't defined p yet, but we're going to later. We know we're going to do that up here, so we can use it here. So we have a pi and a p. And then for the 0 term, we're just saying let's import 1, which is a symbol, the element with 1 set. This is what Greg was using. But this just means we need 1 sort of base element, our 0. And then we have m and n here, which are both just n's, right? So both m and n are defined here. So we have an n cross x, nx cross nx.
So is 1 a set and 0 is a member of that set? Or how does that work?
Yeah, so that could be a way that we do it. We don't necessarily have to define the members of these sets in this definition here. That's just sort of one way we can think about this equation, is certainly that 1's a set and 0 is the only member of that set, but that's not strictly necessary.
Okay.
Jake,
Yeah.
I don't mean to take us off course, but can you remind us why do we do this in the what's our purpose of creating these mathematical models?
I guess our purpose of creating these mathematical models is just so that we can study these language constructions mathematically. I don't really. I haven't seen them used anywhere, but I also haven't been spending a lot of time studying these things. Does anyone else have any insights there?
Me personally, I like this kind of notation as it tells you something about the structure of the expressions. I might be wrong there, but it's kind of pretty good intuition for me.
Yeah, it's right. Sure, certainly. Yeah, it's one way to express the structure. So some people like to read, Scala case classes, and can see the structure very clearly from there. Other people, might want to, study and see the mathematical structure. I mean, it also allows us to sort of use all of these notions that we have from set theory when we're looking at, which is like a well-defined discipline when we're looking at our language constructions.
I see. Okay, so I guess if you want to make statements of fact about the language, you can know that you've covered all the possibilities in this mathematical model. Is that kind of a way of saying it?
I think so, yeah.
It's nice for people like me that have a stronger math background than Scala background too. It helps me kind of wrap my head around it.
Okay.
And it's also used to come up with the reduction rules, right? Because once we know how to go from one symbol to the other, then we can use them in algebra and reduce one term to the other.
Yeah, that's true. There's you can look at this not only the structure of valid sentences, but the structure of transformation of those sentences.
Okay, thank you. That helps a lot.
Yeah, awesome. Thanks for the input, everyone. All right, so and then we have the last one here. I think this should be decently clear. At least if the other two examples were understandable. What questions do you have here about the mathematical model of the PyCalc grammar?
I guess, for example, earlier we mentioned how bang means sending something, and when it gets converted into math, we're just doing the disjoint union. Do we have any concept of it being sent somewhere? And so how does the math kind of map onto what's actually happening in the computer?
Sure. So this math is not mapping on to anything that's happening in terms of the semantics of our language. So we know nothing about sends. We know nothing about receives. We don't really know what these things do. We're just saying that if you wanted to write down every single valid program that you can think of, and it doesn't matter what those programs do, you don't know what those programs do yet. What would that look like? What would that set of all valid programs look like? And this is how you can see that set of all valid programs. So they're not executing yet. We're just defining our language, right? So it's like learning all of the words in French, but not knowing what any of them mean. But you have a French dictionary.
Very meta.
Yeah, exactly. Yep. Okay, and then in the class, we also went over the mathematical model of the RChain grammar. And the interesting piece of this comes in down on the second line. So we're saying that RP is actually our construction for row calculus processes. And RP doesn't depend on any set that we're importing at all. It's not parametric in anything. And RP is actually what it's going to be is this process construction that we have defined with RP itself. So row calculus processes themselves serving as the names or serving as the set that we're importing as we're defining processes. So let's say we want to construct a valid rolling process. We say, okay, right now our set of RP contains 0 elements. We don't know what any of these are. So we're gonna look and see if we can define these things. Okay, so we have P of RP. So we need to look at the definition of P, and we need to import a 0 element set. So we have nothing for X yet. And we're gonna go up here and see if we can still do anything, even if we don't have any X's. So we have P of X, where X, we have no elements of X. Now, which one of these things can we still construct?
The leftmost one doesn't have any X's in it.
Right. So we still have a valid term. So now we have and that term is the process 0, right? That's our first element that we have that on which everything else is built in row calculus. So then we can go back and we can say, all right, so now we want to define another process, RP. And this time our set RP already contains one element set. It already contains a construction, which is the 0 process. And we want to build something else. Okay, so now we have P of RP, and now we can come back up here, and now our X has 1 element in it, and now we can construct, I think, any of these terms. Yeah, we can construct any of these terms now.
So if I want to construct that second one, X cross P of X, that came from the 4, so far we only have 1 in our RP, which is our set of X's, right? So I mean, what does that mean? Is it valid to do 4, 1 from 1, and then the process is 1?
Yeah.
Okay. Oh, cool.
Yep. So it would look like, yeah, it would look like the actual process would look like 4, and then at 0 from at 0, and then the process 0.
Got it.
Cool. What other questions do you have?
RP is a rolling process, but I thought X and Y were names, so I'm a little confused.
Yes. So our RP is a row process, and X and Y are names. So in row processes, so here's a process. Here's right here. This top line is the syntax for a language in which we need to import some notion of name for X. We need to import some set X. Now we say, given that, we can construct something called a row process, which doesn't have to import any sets for names. And what we are going to use to construct that set is this line above. But for these X's, for our notion of name, we are going to use the set of rolling processes themselves. So this is processes are names. Processes, yeah, names are quoted processes. That's what this says. Cool. All right, moving on. I think we might go a little bit over today. Okay, so then we were given, actually, yeah, I'd like to get to the KFramework stuff today as well. So I think I'm going to go over the KFramework stuff right now, and then we can go over the Scala models after that. All right, so KFramework, programming languages usually have a formally defined syntax, but the semantics are usually given in the form of a reference manual, sort of in non-formal English, and we just sort of trust that everything works out and that our programs are going to run as intended. KFramework is a way to formally define both the syntax and the semantics of our program. So that's a pretty cool idea. So that means that not only will we know how to, using KFramework, we can write a definition that not only do we know how to construct the set of all valid programs, or how to check if given program is valid or not, but we can also reason about what that program actually does. So the uses of KFramework used to explore prototypical languages like Lambda calculus, SystemF, agents, formal definitions. It's used to give formal definitions for C, Python scheme, OCL. It's been used to define type checkers and type inferencers. Can be used for program verification, model checking, and researching runtime verification techniques. It's a pretty powerful tool. So let's write our first definition. KFramework, your definitions to be modular. So the way that you define modules is you have module, give it a name, and then end module below that, and then your definition of that module is going to go in between. And so for our first definition, let's define a simple expression language that can either be, oh man, shoot, something. I must be working on an old version of the slides. I thought I fixed this. But we can either write a number like 1 or 4,243. We can add, multiply, or divide numbers. Putting them together, we want that to be a valid expression in our language. We can read a number from the console, and for that we'll just use read. And then print a number to the console. For that we'll use print, and then in parentheses the number that we want to print. So for example, this should be a valid program. We want to print the number that is contained by this process. So reading something from the console, multiplying it by 3, and then actually in this language here, it's not really defined what happens first, if this 1 plus that happens first or this division happens first. And so it's, yeah. But we want this to be a valid sentence. So here's how we would write something like that. We have module exp syntax. So we're gonna separate, since KFramework sort of use modules to define the syntax and the semantics, we're gonna separate those out so that we know when we're talking about one versus the other. So we're gonna have just a module for this language exp, the syntax. And this is sort of the meat of what we're doing here, this syntax exp. So we have some exp that we're constructing. This can either be an integer, and we're using the definition of integer that's sort of built into KFramework. So we're importing it here. We're importing the notion of integer that KFramework sort of comes, that KFramework comes from. So there's some other module somewhere in the KFramework internals that is helping us define integer. And then we're saying, or we can take, if we have 2 expressions, we can add them together. And they could be the same expression if we wanted. We can multiply them, we can divide them, and then read is a valid expression. And then here we're saying that the word print followed by any number of any amount of white space, followed by something in quotes that can have white space around it, with an exp in the middle, that's a valid statement. And then we're also saying that we can just sort of group, if we have a valid expression, we can sort of group that together with parentheses yeah. So let's just do a quick, let me change over what I'm sharing here. All right, can you see my terminal?
Yes.
Great. So here I have exp.k. This is the same file that we were just looking at. And if I have KFramework installed here, so I can compile exp.k. And then we wait for a little bit for KFramework to do its magic. And we wait a little longer. All right, then this looks like it was successful. And then we can this directory has been created, exp compiled, and it contains a whole bunch of stuff, and I don't really know what everything is in here yet. But it contains a whole bunch of stuff that we can use, that KFramework can use. Then we can have our program, so we can write our program example1.exp. So exp was the language we defined, so we can give that the file type at the end. And here is, the example that I said should parse in our language. So KFramework should be able to parse this and tell us it's a valid program. So the way we're going to do that is we're going to do krun example, and we have to be in the same one. Krun example 1.exp. So this is going to use the language definition that we just compiled to try to parse this example. And then what we see is that this was parsed successfully. So we're given this K cell, which is sort of where the computation is going to take place, but we haven't really defined anything about what these K cells do yet. That's going to come in handy when we start defining our semantics. And we can see that it decided to parse that this read times 3 happens, and then that happens with the read times 3 divided by 4, and then we have the 1 plus, and then we print the whole thing. So that's what we want to see.
Jay, can you show us the input that the example.exp real quick? Because you're saying the parens are different, right?
Yeah, so there's the example.exp. So I didn't put any parenters. Yep.
Cool.
So I was sort of unclear as to whether I wanted that construction to happen or that construction to happen, right? And it chose to put parentheses around this stuff. So it sort of looked at this division symbol before it looked at the plus symbol.
Gotcha.
Yep. And I'm having some trouble right now with defining precedence orders for the PyCalc definition, but I'm hoping that we can maybe resolve that together.
I thought I saw somewhere in one of their tutorials that there were like square bracket annotations that would do something like whether things are. I don't know exactly how it worked. I just kind of think I remember seeing that.
Yeah, so I think the square bracket stuff is sort of like some little sugar that you put on top of your grammar that sort of starts driving at the semantic notion. And I don't know if it actually really has any effect on the syntactic notion.
Okay, gotcha.
Yeah. So now here's an example 2. That should be an invalid program. 1 plus hello. We don't know how to parse hello in our language, so this should fail. So let's try to do another krun with example2.exp and see what happens. All right, so we get an error, critical, parser returned a non-zero exit code. So this is an invalid construction. Parser, scanner error, unexpected character sequence. So cool. Yeah, any questions about that demo?
I think a lot of people might be going to try to follow along with this afterwards using your Docker image. Are you using that now, or is this locally installed? And can you show us how to do it with your
Yeah, so I am using the Docker image. I'm not using it in the same way. Yeah, there's a couple different ways to run Docker. So what I've done is I've actually executed a bash script inside of my Docker container, and that's what I'm working off of here. The other way that you can do it is just specify a run. So in my yeah, let me pull up the repo here and show you how you would do this. Oh, let me share my screen. Nope, there we go, this one. So I think I'd probably recommend doing things this way, so you just can like preserve your definitions and stuff that I have in here, unless you want to talk to me about how you can set up like persistent volumes. And it's not hard to use it the way that I'm using it, but I think this is a little bit easier. The command is longer, but so what you can do is you know, how I was saying, like compile and krun and all that. Basically, if you use this command that I've given here, and then this last piece, you just change to whatever command you want to run inside the Docker container. So compile lambda.k, or here, this is the same. All of this is the same, except for this last piece is changed to krun. In this case, in this example, would have been example1.exp. Does that make sense? So you should just be able to copy this command directly, and then change in this last portion, and that will be the command that runs inside the container.
Yeah, totally. Thanks. I just think it might help people follow along if we try to do it afterwards.
Yeah, cool. I guess I will keep going. I'm gonna go a little bit over and go over the Scala stuff, and then maybe at the end of that we can also run the same EXP examples this way. Does that sound good? All right. All right.
Okay.
Yeah.
Was that it for KFramework?
That is it for KFramework. Oh, I guess I'm giving you guys homework too.
Well,
So
I was just I missed how that provided something about its syntax, its semantics.
We haven't yet.
Oh,
we
okay.
haven't yet. So right now we're just defining the grammar in terms of KFramework. In future sessions, we're going to start going over how to define the semantics as well.
I see. So you annotate that with semantic information. Okay, later.
Yeah.
Got it. Thank you.
Later. So yeah, I'd like you all to try to do use everything in this lecture to try to define a PyCalc syntax in KFramework. And you can use this. There's a definition of lambda calculus, a tutorial that you can look at to sort of help you along if you need it. And then we can go over that next week, I think. Oh, what happened here? Huh. Clicking on that link did some weird stuff. How do I get back to? All right. All right, so Scala models of grammars. So we have our construction of lambda calculus again. And what we are going to do is we're going to define this class or this trait mx, which signifies our programs, just like we were seeing it before in the mathematical model. So m is a type that is parametric in another type x. And then for our first, we have this first option here, we have a case class mention, also parametric in x. It requires one x, one x from large X of type large X, and it extends mx. So it is this is a way that we can form. This is one form of mx. Another form of mx is here. We'll call it abstraction, and it takes an x of type x, large X, and an m of type mx. So sort of this little m is mapping to that guy, and then this little x is mapping to that guy. Application, same thing. So this was the example that Greg gave in his course. What questions do you have on this? Okay. Oh.
I think I'll just point something out real quick. One thing that I was really tripped up on was that I think on Greg's slide, he accidentally omitted extends MX from that last line, that application line. And I spent a lot of time trying to figure out why that one was different. And I think maybe it was just a mistake now.
Yeah, yep. I'm almost certain it was.
Cool. That helps a lot. Thanks.
So Scala model of our simple grammar that we had above, you know, we can do a similar thing. We can call this construction lambda that takes an x. We can call this construction triangle that takes an x. They both extend our simple language, which is parametric in this notion of x. And then here's the Scala model of our PyCalc grammar. This is where things get a little bit fun. So I think this constructing this par, the replication, and the new x is all pretty much exactly the same as before. Oh, I guess new is a Scala keyword. I probably shouldn't have used new there. So this probably wouldn't compile. But then what we have when we get to this guy, so this is the same format, you know, that we see here in this paper. I'm just trying to follow that as closely as possible. Now we have these other symbols. We need to somehow express this summation in our language. So first, we're going to need to define what these pi's are. So we have a pi, also parametric in x, and we have inputs and outputs of those pi's. They take two names, the subject and object. Okay, again, I'm using Scala keywords, so this probably wouldn't compile for variable names. And then using that definition of pi, we can give a definition for this summation. So the summation, what we're gonna call it, is a set of tuples of type where the first element is a pi and the second element is a process. So we sort of embedded this more complex type, and this would contain inside of it, right, inside of this construction for the normal process, the code that actually sort of does this, you know, we would define that if this set has 0 elements, that would be the 0 process, just as sort of it's written. Where is that written? So in the paper, I don't know. It says it in the paper. Oh yeah. So here it says, right, the case where the set I that we range over is empty. So in this summation is a summation of 0 terms, we would write that sum as 0. So that would just be sort of an implementation detail. And that would be an expression of our PyCalc grammar. What questions do you have here? Okay, and then, so yeah, for next week, I think it would also be cool to do, well, this was given as homework in Greg's class, is a Scala model of the RChain grammar. So I'm not going to, I haven't actually done it yet, but I also am not planning on giving out the answer here unless we go over it in Greg's class as well. So yeah, hopefully those examples sort of help get you closer to the RChain construction. RChain grammar. Okay, that is all I have for this week. Thanks for hanging on for the extra 15 minutes. Oh yeah, and then yeah, what questions do you have for me, or what items of discussion do you have? All right, if nothing.
Oh, Jake, sorry. I just found it interesting that you you represented the empty process as this empty set.
Yeah, that's how they do it, at least in this definition here.
So do you think the classes you've defined there would be used as the abstract syntax tree, or is this something else? This is like this. Is that different? The classes you've defined? Would you actually parse into those types?
I think you probably could. Yeah.
Okay. Okay. Thank you.
Yeah, right. So, I mean, that gets into like, you know, when there's some valid programs that we could write that when we parsed them, we would sort of be erasing some details, right? So sets can't have two elements that are the same in them. But if we have two elements that are the same in this construction, it actually is semantically the same as there's no semantic difference, right? So when we do the reverse process of going maybe from the if we use these types to process the syntax tree, we would take some text file, which is our program of PyCalc program, parse into the syntax tree, and then if we did that reverse process, we wouldn't necessarily end up with the same text file, but we would still retain the same meaning of the program. And the reason for that too is that the plus, the addition construction, says that only one of these things happen, and then in PyCalculus only one of those only one of these pi.pi's actually happen, and then the rest get eliminated. Okay, so that
interesting. Thanks, Jake.
Mm-hmm. Okay. Yeah.
So I wanted to say thanks. This helped me a ton. These are really educational for me. So I appreciate all the work you're putting in. And then before, I think when you close the session, the chat goes away. So I just wanted to be sure that we know. I think Jake, you have to be the one to do this. It looks like maybe session 5 is missing from the repo from the PyCalc one. I just saw that came across the chat.
I'm not seeing the chat. Huh. Oh, thank you. Okay. Yeah, I think I do get to retain the chat, but yeah, all right, I'll make sure that.
Cool.
Oh, okay. Oh, Kayvon is telling me. Okay, CLJ. All right. Yeah. Great. Session 5. Oh, yeah. So session 5. Yeah, I haven't uploaded that to the repo yet, but it is the YouTube video is available in the playlist. But I just haven't put the information there yet.
Oh, okay. Okay. So if the video's up, I guess anyone can do it then too.
Yep. Okay. Then, yeah. Anyone feel free to jump off at this point. I'm going to give just so we have it for video, or people who are interested, run the same EXP examples, expression language KFramework examples, just using the Docker image in the way that I use it in the GitHub examples. Okay, yeah, thanks everyone for attending.
Thanks for the lesson. It was very useful.
Thanks a lot.
For the homework for Greg. See you later.
See ya. All right, so I'll share my terminal again. Let's see. I might actually use okay. So here I have, I'll just use the Lambda example, actually, just because I don't have the EXP written out as a file here. I could copy it over, but I don't want to force you guys to sit through that. Actually, no, let me. All right, so so I'm going to make a directory exp, go into it, and then I'm going to write a file, exp.k. I'm going to copy over. Let's just find that KFramework definition that I wrote. Okay, so here is our expression language, and then we can, it's a big long command. I can maybe go through what the command is doing too. That might be helpful. So the way that I have Docker installed, I need to always sudo docker. You can change, yeah, if you're having troubles, you might want to try that. Otherwise, you can add your user to the Docker group on your system. In Linux systems, I'm not sure how Windows handles the permissions and stuff. And then what I want to do is I want to run a Docker container, and I'm going to use the user dev inside of that container is what I'm going to, is the user that I want to be running as. And then my Docker image has like an entry point that runs just a simple bash script to keep the Docker container running all the time. But if you want to use it just to run a simple example, you want to clear out that entry point so that the container doesn't keep running after the process finishes. And then what I want to do is I want to bind the volume, which is my current working directory, to this specific place in the Docker container, which is this folder in dev's home directory called playground, which is just an empty directory. So what that's going to do is any files that I have in my current directory that I'm executing this command from are going to be mounted, are going to be available inside the container at this location. And then this is the image that I want to run. This will automatically pull the image from Docker Hub, so you don't need to do any Docker pull or anything before that. And then this is the command I want to run inside of the container. I want to run a bash script with the login option so that it sources the profile that I wrote, so that you make sure that all the KFramework stuff, all the things that I've installed are correctly on your path. And then the commands that I want to run inside of that bash script are here. So we first cd, change our directory to that playground so that it sort of looks like we're running in our current directory. And then anything that the Docker file, anything that the Docker image writes to, or the Docker container writes to playground, it's sort of both a read-write, so that will come back to the current directory that I'm running this command from, so we can see the results. And then after I change to that directory, what I want to do is, this is where I specify the command that I want to run inside of the container, so I'm going to compile exp.k. I need to type in my sudo password. Gotta wait. our command finished. So now we can see that we have this directory exp compiled written in the folder that we ran the command from, the directory that we ran the command from. Now we can create an example. So let's just do 1 + 2. It's a good example program. And we can go back up to the same command. And this time we want to do a krun example 1.exp. And there we see that everything parsed correctly. Now we can create something that isn't a valid program in our expression language. And we can try to krun that. And we find the same error. So yeah, that is how you will run using the Docker container in this method, in this way. What questions do you have here for the couple people who are left? All right, thanks for watching. See you guys later. See you all later.
Thank you, Jake. Have a nice weekend. Bye-bye.
Thanks.
Thank you, Jake.
Thank you so much.